In this problem, you are asked about the number of positive factors that this big number has. This is actually a very basic problem. As I mentioned multiple times in my past videos, that when students prepare for these AMC8 or math count or AMC10, 12 kind of math exams, prime factorization is a very powerful tool, especially in handling number theory problems. And here is another example. The beauty of prime factorization is it can break down a large number into smaller pieces. So first of all, we need to know how many pieces or what kinds of pieces that this big model has. Now let's look at this problem. We want to prime factorize it. So let's get started. So we have this 23,233. That's a large number. So we will break this down little by little. So certainly we realize that the last two digits are divisible by 4, then the whole number is divisible by 4. So we have 2 to 2 times, we'll do it here, 2, 3, 2, 3, 2. So when that is divided by 4, we have 5 here, 20, 32. So we have 8, right? That's 32. And the 3, so that's 0. And 2, that's 8. Good. We have 2 to 2, 2 square times 5808. Again, the last two digits is divisible by 4. So 2 to 4 times 5808 divided by 4. So that's 1. We have 1 here, 18, 4, 16, 20. That's 5, that's 2. Good. We have this 1452. Again, this is divisible by 4. So we have another 2 square. So 2 to the 6 times 1452 divided by 4. So that's 3, 12, 25, 6, 24, 12, 3. Good. Now this is our number. We can't play with these bunch of factors of 2. So then what next? Certainly this is divisible by 3, because the sum of the digits is divisible by 3, so the whole number is divisible by 3. So this equals 2 to 6 times 3 times 1 to 1. Do you recognize this? That's 11 square, right? So that's 2 to 6 times 3 times 11 square. Now we complete the prime factorization. Then what's next? The question is not directly about prime factorization. How should we use these prime factors? As we pointed out, these prime factors are like the building blocks of a Lego model, right? These are the smallest piece that you can't break anymore. We have 6 of this piece, 1 of this piece, and 2 of this piece. Now we want to use some of these to build some smaller model. A smaller model means it's a factor of this original large number, right? Then let's start from 2. So to construct this factor, we need to pick some 2's, right? We need to pick, let's say this is K1. Then this K1 can certainly equals 6. We pick all of them, right? Or we can leave out some. So we can pick 5, 4, 3, 2, or 1. Is that all? No, because we can certainly skip this piece entirely, which means not picking it. So that'll be 0. Then let's look at the next piece, 3. For 3, let's still denote the exponent of 3 is k2. Then what kind of values that k2 can take? So the max we can have is 1 of this piece of 3, right? So k2 equals 1. Or we can simply skip it, not using this piece. So that's 0. And same thing for 11. Let's say that's k3. So for k3, we can pick both of this 11 piece. Or we can just pick one of it, or none of it. Therefore, we have so many possible choices. That's 7, that's 2, that's 3. And if we multiply them, we'll get the total number of factors that we can construct for this number, for this big number. Just to give you an example, let's say 2 to the 4, and 3, let's say to 0, and 11 to 1, right? This is certainly a factor of this. And this is certainly the original number. Therefore, the solution is 7 times 2 times 3. So this gives us 6. So 6 times 7, that's 42. Therefore, the answer is E. Then before we end this video, I just want to generalize this problem. So let's suppose we have an integer, a positive integer, right? And suppose this integer can be prime factorized into this case. Let's rank the prime factors from the smallest to the largest. So P1 to K1 times P2 to K2 times ... to Pn time to Kn, where P1 is less than P2 less than ... less than Pn. Pn is the largest, and all primes. And the Ki should be all non-negative integers. We'll use this notation. Good. So as long as n can be prime factorized in this way, then we know the total number of positive factors of n equals k1 plus 1 times k2 plus 2 plus 1 times, this is 1, times ... kn plus 1. And the proof should be very straightforward, just like our analysis here, right? For the first prime factor P1, we can pick all of it, or part of it, or none of it. So that's K1 plus 1 many choices. And the same thing for each of these prime factors. And in the end, when we multiply all the numbers, this is the final results. If you like this video, please give a like and subscribe the channel. If you have questions, please comment.